Good morning, students. So we'll move on to the next topic, that is Moore machine. So in previous lecture, we discussed what exactly a transducer stand for. Okay, and along with that, we discussed what is melee machine, fine, how it is going to be projecting the output in the particular state. Okay, regarding that, we had a complete discussion, right? So here also we are going to discuss about the same variety of a machine, okay, and same kind of problem also we are going to discuss, fine. But there is a slight change, okay, when we are comparing with melee machine and Moore machine. The outcome will be same, but in case of melee machine, the output will be projected. Output will be projected along with the input exactly, right? Whenever we were having a arc from Q0 to Q1 or Q0 to Q0 itself, okay, if that arc is labeled as 0, fine, the output of that will be labeled with what? Forward slash, odd, even, okay, such kind. Fine. The melee machine will be projecting the output along with the input exactly. Okay. But Moore machine, the output will be associated with the state name exactly. Okay. So when we solve the first problem, then you will be getting a complete knowledge about how this state will be projecting the output. Okay. So now we'll go through the definition of Moore machine. Okay. We know already what exactly transducers stand for. Fine. The state, if it is projecting a output along with the input, okay, then we are calling it as a transducer. Fine. So these are the problem, the same problem we solved along with the DFA method. Okay. So if you are feeling some difficulty for solving this kind of problem, first you solve that problem using DFA method. Clear? Fine. Okay. Solve it using DFA. Then just remove the final state. Clear? Then you will be having the complete skeleton of melee machine and the Moore machine. Clear? Then the output projection, in case of melee machine, it should be projected using input alphabets. Okay, but in Moore machine, it should be projected using states exactly. That is what the only difference. Okay, now we'll go for the definition. So in this session, we will be discussing like what is Moore machine and examples of that. Okay, what is Moore machine? A finite state machine where an output is associated with each state is called Moore machine. Okay, formally, it is denoted as machine M will be equal to Q, stand for what? The total number of states. Okay, the sigma, comma G, comma delta, comma lambda, comma Q naught, where Q is the finite set of states, obvious, like how many different states are getting involved in this particular designing of a Moore machine. Okay, that will be considered using a Q exactly. Then the input alphabets like A comma B or else 0 comma 1, okay, or any other alphabets if you are using, okay, as a input for that particular Moore machine, fine. So that will be named under sigma exactly as usual. Okay, then we have a G symbol. It's a set of output alphabets. Okay, so according to the question, if they're asking for even and odd, then the output alphabets will be E and O. We are considering it as, okay. Sometimes we were calling like complement of that. Okay, so it depends on a question. Fine. What they're expecting the output, according to that, we need to decide what should be the alphabets of G exactly. Okay. Then later, the transition function, the delta, as usual. Okay, like Q cross sigma to Q. Fine. Like if you're feeding any one alphabet for a particular state, so it will be providing some return value over there. Okay, so that will be represented using delta exactly. Okay, then lambda we are using for what? Output functions exactly. Okay, so the output functions also we need to decide over here because as we discussed in previous melee machine, we are designing two different transition tables over here. One is for the delta and one is for the lambda exactly. Okay, so like that here also we need to design. That's why lambda we are using. Then the start state will be obvious Q naught. Okay, we are beginning with the Q naught state. That's why Q naught will be the start state. Now let us see how to construct a Moore machine by taking some specific examples over there. The same example, okay, the three problem what we discussed in the previous lecture, same we are considering. Construct a Moore machine which accepts strings of zeros and ones, output even when the input string has even number of ones, and output odd when the input string has odd number of ones. Okay, so here I want to repeat, like they are saying a sentence like which accepts strings of zeros and one. Okay, so please don't get confused, like they are asking us to make some string to get accept over there. No, it is not a string. Okay, it is consisting of what zeros and ones. Okay, the string will be having an alphabet called as 0 and 1. Okay, so that should be accepted by your mirror machine exactly. That's it. Okay, like 0 should be accepted as an input. 1 is also should be accepted as an input. Okay, so now what the condition they are expecting or they are proposing here is like whenever we are having even number of ones, then state should project the output as what? Even exactly. Okay, if we are having odd number of ones, then the state should project odd exactly. Means if any particular state receiving a input alphabet as a 1, okay, how many number of ones you are having here? Only one, right? How many number? Only one. Okay, so 1 times 1 has occurred. It means what? Odd exactly, right? So there, wherever we are having a possibilities of odd number of ones occurrence, okay, there we need to project the output as odd exactly. Then where we are having a possibilities of expecting even number of ones, there we need to there we need to project even exactly. Yeah. Okay. So now we'll go through the solution. The FSM, which accepts strings of zeros and ones as the input, accepting even number of ones, can be written as shown below. Okay. So even number of ones and odd number of ones. See here, uh, like we got two different states. Okay, Q0 and Q1. So we can create a loop for 1 exactly. See here, we are discussing about only 1, right? Okay, we are not discussing about 0 exactly. The minimum string is what? Even number of ones or odd number of ones exactly. See, when we get, you may ask like, sir, even will be two number of ones and one number of ones we need to consider. Then 2 plus 1, 3 different states we need, but here we are using only 2 exactly. See, if we are having 0 number of 1, that we are considering it as what? Even, right? Okay, when you are having 1 number of 1, then we are having odd number of ones exactly. Okay, so here 0 is the minimum string and along with that 1 is the minimum string over here. Okay, minimum number of strings 0 comma 1 exactly. Okay, so here to deal with 0 and 1, how many number of states we need? 2 number of states we need, because n plus 1, okay, means 1 plus 1 will be equal to 2. Because of that we are having 2 states over here. Okay, so now Q0 and Q1. So odd number of 1, if I want to make it as accepted, then this will be the final state, right? Because here odd number of ones. Then even number of ones, if I want to make, then it should be a reverse loop. Then Q0 should be made as a final state over there. Then even number will be accepted if I make Q0 as a final state. Q1, if I make it as final state, odd number of ones will be accepted. Then what is the see here, for Q0 transition for 1 over, for Q1 transition for 1 over. But Q0 and Q1 both are having left with 0 transition, right? So 0 transition for alphabet 0 exactly. So we are providing a self loop over here. Okay, because we don't have issue with like how many number of zeros we are counting, well, like we are having available. Okay, even number of or odd number doesn't matter. Okay, so now so this place we are projecting it as even and this place we are projecting it as odd exactly. Okay, so note we have observed the following point. In state Q0, the machine accepts strings of zeros and one having even number of ones. So associated state Q0 with output E. Okay, so E is the output. We need to associate with Q0 exactly. Then later, in state Q1, the machine accepts strings of zeros and ones having odd number of ones. So associated state Q1 with, so associate state with what? 0, sorry, O exactly. It states odd. Okay. So previously, what we used to do is, in case of Melee machine, here we need to represent as E exactly. Okay, and here we used to represent odd. Here we need to represent it as odd, and here it should be represented as even. Okay, if you want, you can go through the previous lecture. Then you will be having better knowledge exactly. Okay, but here what we need to do, in case of Melee machine, we are not projecting the output along with the input. Okay, output will be projected along with the state exactly. Okay, so how it will be? Q0 is the state and Q1 is the, it should be Q1 exactly. Okay, it should be Q1. They made a mistake. Okay, Q1 exactly. So Q0 with what? Even location, right? So Q0 comma E exactly. Then Q1 comma 0 exactly. 0, so not 0, O exactly. Okay, the rest of all will be same. Fine. So this is how we are creating the Melee machine exactly. Only difference is what? Instead of projecting the output along with the inputs, okay, we are attaching it with state exactly. So Neta, the second problem, same problem, like we need to identify how many times we got this AB pattern. Okay. So for that, what we do, like first we are designing a DFA, which is accepting the state, sorry, which is accepting the pattern, which is ending with AB exactly. Okay. If I see, you may ask like why we need to go for this ending with AB. Okay. Remember, if you are having a string like fine, like how we discussed in the previous problem. Okay, same thing we cannot follow over here. See, if you are having a string like A, B, 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 A, B over here. Okay, so if you are dealing this first AB or any AB, okay, before this end, okay, with any particular states and all, you will not be having a clear picture like how many times AB we are going to get. Okay, so what we can do is we will make this, we will design a DFA so that whenever we get AB, it should go to some particular place. Okay, and that particular place, we can provide some tracking system. Okay, so from there we can count like how many times the pattern AB has occurred. Okay, the best suitable way is what? We can consider a DFA which is accepting the string of what? Ending with AB exactly. Clear? Ending with AB means what? Whenever you are getting that particular AB pattern, it will be moving towards the final state exactly. Fine. After that AB, if any other string is or either any other alphabet is available, it will go to some other location. From there again we are concentrating like whether we are getting a AB or not. Okay, then like how many times we are approaching the final state, those many number of times the AB pattern is occurring. That is what the logic we are using over here. Okay, so now we'll go through this. So here the same thing using a DFSM, okay, like deterministic finite state machine or DFA. We are designing this particular DFA skeleton. See A, B. Okay, whenever we get a pattern AB, then it will be going towards Q2. This we discussed in DFA topic and also in the Melee machine also. I don't want to repeat it again. Okay, then what we need to do in case of Moray machine, what we have to do, we need to remove this particular final state double circle. Okay, it should be named as normal Q2 itself. Okay, so like here, if you are representing A, then it should be called as 0. Here, if you are representing with B, it should be also called as a 0. Okay, but in case of a final state location, it should be called as a 1. Okay, whenever we are reaching the final state, that represents like we encounter pattern AB exactly because of that. Okay, so what we do, Q0 comma 0, Q1 comma 0, Q2 comma 1 we are writing. Okay, so here we got one example ABB AB. Okay, see here how many times AB is occurring? Once and twice exactly. Okay, so if you're following this, see Q0 on receiving A, it will be going for Q1 exactly, right? Okay, what is the projected outcome? 0 exactly. Then Q1 on receiving B, it will be going for Q2 exactly. What is the outcome? See here, the output, see Q0 is associated with 0 exactly, but here this 0 states Q1 exactly. Okay, to where we are moving, right? Q0 to Q1. Okay, Q1 is associated with what output, right? Along with this state, that should be written over here. Be careful. Q1 on receiving B, it will be going for Q2. Then Q2 on receiving B, see, we are coming back to Q0. Q0 is associated with 0. That's why we are writing 0 over here. Then again, Q1 with A, then Q1 with B will be 1 exactly. So how many number of times we are getting this 1? Twice exactly. Means in this particular string, twice we are finding a pattern of AB exactly. Okay, so that is what how we are dealing with this particular question using a Moray machine. Okay, then the last problem of module number 1. So this is the last problem. Okay, so construct a Moray machine which accepts a binary number and produces its equivalent ones complement. Okay, so the same variety we are using. Okay, how we discussed in the Melee machine, same kind exactly. Fine. Observe it very careful. Like we need to convert 0 to 1, 1 to 0 exactly. Okay, so while designing this Moray machine, okay, we need to transfer or we need to have a transition for 0 towards one state, okay, for 1 towards another state exactly. Okay, then if you are projecting, see a very simple example, okay, Q0, see, he is responsible for what? 1 exactly. See, Q1 on receiving 1, it will be going for Q0. Q0 on receiving 1, it will be in Q0 itself. Means here we are dealing with 1 exactly. And here we are dealing with 0 exactly. So if you are projecting the output along with the state for Q naught, if it is 0, then we can get complement of 1, right? Complement of 1 will be what? 0. Then in case of Q1, we are dealing with 0 exactly. Complement of 0 will be what? 1 exactly, right? Okay. So if you are projecting Q naught comma 0 and Q1 comma 1, then easily we can have a complement of 0 and 1 exactly, right? Okay. See, if this is what the pattern, string pattern 1 0 0 1 0. Okay. Then see Q naught on receiving 1, it is going for what? Q naught itself. So what is the associated output? 0 exactly. See, Q naught is associated with 0 exactly. Then later, Q naught on receiving 0, it will be going for Q1. Q1 is associated with 1. See, 0, 1 we had, 0 we got, 0 we had, 1 we got. Then now, again we have 0. So Q1 is having a self loop for 0 exactly. So this 0 will be complemented, okay, to 1 exactly. So 0 complement 1 we got. Then Q1 on receiving 1, it will be transferring it to Q1 exactly. Transition will be having. Okay. So Q1 transfers 1 to Q naught. Okay. Change of state. So Q naught is projecting your what output? 0 exactly. So 1 complement 0 we are going to get. At last we are having a 0. Again it will be sent back to Q1. Okay. So which will be the complement of 0 we are projecting, or we are having the associated output 1 exactly. So for the input alphabet 10010 for the this particular, using this Moore machine, we can generate a output called as what? 01101 exactly. That is what the complete complement of this particular binary pattern. It is not only for like only 5-bit binary pattern. Okay, if you are having a 1000-bit binary pattern also, doesn't matter, it will generate the complement output. Okay, so this is for our students. Okay, so we'll meet with the module number 2. Okay, in next video. Thank you, students.